Okay, so at the end of the last video, we were just talking about how sampling distributions of sample means, and as the sample size increases, now this is the sample size, remember that we said for each individual sample that goes in the sampling distribution, then the distribution of sample mean changes its shape. Okay, so if we have large sample sizes, if the population distribution is not normal, it will look like a normal distribution. So when the sample size is large enough, the distribution of a sample mean is very close to normal, no matter what the shape of the population distribution is. Okay, so a couple of things. Number one, for sampling distribution of sample means, if the population is approximately normally distributed, so you took the whole population, put it on a curve, normally distributed, then your sampling distribution of sample means, no matter what each individual sample sizes, will be approximately normally distributed. Okay. However, if the population is not approximately normally distributed, the sampling distribution of sample means can still be normal. Okay, and how will we know if the sample size is large enough for it to be normal? So if we take a simple random sample of size n, okay, so let's say of size 15, from a population with mean mu and finite standard deviation, so that just means that you're not looking at an infinite amount of people in Fairfax County. There's at some point there's going to be the end of people in Fairfax County. Okay, the central limit theorem, and you may have heard of this in some of your other classes, the central limit theorem, this is going to be really key to sampling means only, says that when n is large, the sampling distribution of sample mean x is approximately normal. So that's like saying if we're taking samples of size 40, finding the mean, putting that on a graph. Take another sample of size 40, finding that mean, put on a graph. Another sample size 40, finding that mean, put it on the graph. Okay, the graph of all of those means of samples of size 40 will be approximately normal according to the central limit theorem. So you might be asking, well, how big does the sample size need to be in order for my graph to look approximately normally distributed? Okay, so let's answer that next question. So how large do we need n to be for the sampling distribution to be close to normal? Okay, now remember that if the population is approximately normally distributed, then it doesn't matter what the sample size is, the sampling distribution will be approximately normal. Okay, so what happens if the population distribution is far from normal, or if the population distribution is approximately normal? Well, we said that if the sample size is large enough, the sampling distribution will be approximately normal, and we're going to take a look and see what that size needs to be. So the sampling distribution will be normal if n is greater than or equal to 30 according to the central limit theorem. So what the central limit theorem says, hey, if you have a population, you graph it, such as income is usually skewed to the right. Okay, you graph the income, it's skewed to the right. Okay, that population is not approximately normally distributed. However, if I take samples of size 30, find the mean income, put that on a graph. Take another sample of size 30, find the mean income, put it on the graph. Take another sample of size 30, find the mean income, put it on the graph. Then the distribution, the sampling distribution of the sample means, all those means, will be approximately normally distributed. So as long as the sample size that you're taking is larger than 30, okay, then the sampling distribution will be approximately normal. So we're going to take a minute and look at the central limit theorem, or the CLT, and see exactly what that looks like, how we came up with the number 30. Is that just arbitrary, or did somebody actually prove why we're using the number 30? Okay, so let's take a look at this graph. We're taking a look at the strange population distribution from Rice University. Okay, now n is the number of samples for the sample mean. So this is the population distribution right here. All right, so this is not, we take a look at this, this is not normal. Like, I don't even know how to describe this, okay? So let's take a look and see, this is the population distribution, that when I take samples of size 2, find the mean, put them on the graph. Samples of size 5, find the mean, put them on the graph. Samples of size 10, find the mean, put them on the graph. Samples of size 25, find the mean, put them on the graph. What happens? Okay, so notice, okay, let's say that I take samples of size 2, find the mean, put them on the graph. Oh, now I'm finding all these means, I'm sort of averaging everything out. And think about it, so if you have this low extreme and you have this high extreme, and you're adding them together and dividing by 2, it's going to sort of put it in the middle. So same here, you have this extreme and this extreme, and you're adding them together and dividing by 2, it's going to put that in the middle. So it's taking all the extremes essentially and adding them together and sort of putting them in the middle. So this looks a little bit better. It's still not normal. Now what happens if we do n equals 5? So this is saying I'm taking 5 of these, finding the mean, putting it on the graph. Taking another 5, finding the mean, putting it on the graph. Taking another 5, finding the mean. You get the picture, putting it on the graph. Now notice the distribution of the means is getting closer to approximately normal. What happens when I take samples of size 10? All right. I took 10 individual values, found the mean, put on the graph. Samples of size 10, find the mean, put them on the graph. And I kept doing that hundreds of times for this graph. Now this looks more approximately normal. Now look at the one when it's 25. Okay, so from up here, all right, I took samples of size 25, find the mean, put them on the graph. Samples of size 25, find the mean, put them on the graph. Okay, so notice as my sample sizes get larger, when I look at a graph of the means, it looks more and more approximately normally distributed. So that's where we came up with the number 30. Okay, so if the population distribution is normal, then so is the sampling distribution of sample means. Okay, this doesn't matter how big the sample size is. So if I took samples of size 2 and the population was normal, then the sampling distribution is also going to be normal. If the population distribution is not normal, the central limit theorem tells us that the sampling distribution of x bar, or sample means, will be approximately normal in most cases if your sample sizes are greater than or equal to 30. Okay, so does that mean if it's 26, it's not going to be normal? Not necessarily. Okay, it could be. So we choose the number 30 because in most cases, when we've tested this over and over again, if the sample size is greater than or equal to 30, it produces a graph that's approximately normally distributed. Okay, so now why do we need the central limit theorem? Why do we need to show it's approximately normal? What it does is it allows us to use the normal probability calculations to answer questions about the sample mean. So to make inference basically from many observations even when the population distribution is not normal. Because remember, we can't use the mean and standard deviation if my population distribution isn't normal. Okay, so now we can use the normal curve to answer questions about probability if we're dealing with sample means and as long as the sample size is larger than 30. Okay, so we talked about conditions in the last section. What conditions do we need to check for sample means? Same exact conditions. Number 1, did we have a simple random sample? That's usually stated in the problem, okay, because remember that if we don't have a simple random sample, then most likely it's going to be biased, okay? 10% conditions, still exactly the same. So this is basically saying that the sample must be smaller than 10% of the population. Population's 10 times the sample size. This proves that each n of the n values are independent and you can use a standard deviation. And finally, this is what's different, okay? With sample proportions, we proved that it was normal the same way we did with binomial distributions. However, for sample means it's different. If the population is normal, then the sampling distribution will be normal. If n is greater than or equal to 30, then the sampling distribution will be normal by the CLT. Okay, so 3 conditions every single time. SRS, 10% condition, approximately normal. And the only thing you'll have to remember is the difference between sample means and sample proportions. Okay, now what are some things to watch out for when we're talking about the central limit theorem? The central limit theorem does not describe how the variability of a sampling distribution increases. So the sampling distribution, or the CLT, the sampling distribution, the central limit theorem doesn't tell us about the standard deviation. It doesn't tell us if it has a lot of variability or if it's really tightly packed together. It just tells us that the sampling distribution is approximately normally distributed. It's true that as the sample size increases, the variability decreases, but that has to do with the standard deviation and not the shape of the data. The central limit theorem only tells us about the shape, okay? It only tells us about whether or not it's approximately normally distributed. It has nothing to do with the spread of the data, all right? So that when the sample size increases, that has to do with the standard deviation. So we use the central limit theorem just to state normal, not normal. Okay, let's just do a quick summary and then take a look at some examples. Okay, here's a summary of sample means. So let's go back to our example where we had 100 seniors in Virginia. So suppose I randomly select 100 seniors in Virginia and record everyone's GPA. I'm interested in knowing the average GPA of a senior in Virginia. So here's my 100 seniors, here's all of their GPAs. Okay, now this 100 group up of this 100 group of seniors make one possible sample. The sample mean, or the average GPA, for this particular group of 100 students is 2.5470. The sample standard deviation, notice the notation S of X bar, is 0.7150. Now keep in mind that this is only one sample of 100 seniors. If I took another 100 seniors, they'd have a different sample mean and a different sample standard deviation. So keep that in mind. Mu is our parameter. So this is our population mean. That's the true mean GPA of a senior in Virginia. Okay. X bar is our statistic. That is our sample GPA, is the mean GPA of a senior in Virginia in a simple random sample of size 100, because this is from a sample. Okay. To calculate the value of mu, we find the mean of our sample X bar. So we use the mean of our sample to estimate the mean of the population. Okay, remember, if we pick different samples, the value of our statistics, or the mean GPA, is going to change because it's 100 different students. If we decide to graph all the values of X bar for all possible samples of size 100, you will have a sampling distribution of sample means. Now, if you, let's say you only do 50 groups of 100, then that's an approximate sampling distribution because it's not all possible samples of size 100. Now, what will our model look like? Number one, remember that each X bar is a mean. All right, so we're going to find all possible samples of size 100. We're going to find the means for all of them. Each of them is a mean. Means are less variable than individual observations because we're only looking at means. We're not looking at extreme values. So when we find the mean of those 100 students, we're not going to see the lowest or the highest. We're just seeing the average of those 100 students. We're not going to see GPAs that are very low or very high, only average GPAs. And that's what contributes to our graph being approximately normally distributed. The larger the sample size, the less variation we're going to see in the values of X bar. Well, why is that? Because the more values we have, the more all of the extreme values sort of average each other out. So as the sample size increases, the standard deviation decreases. But remember, that does not have to do with the central limit theorem whatsoever. The central limit theorem just tells us the shape of the graph. If the sample size is large, it's going to be approximately normal, so greater than 30 by the central limit theorem. Okay, if the sample's from a normal population, then the sample means will be approximately normal. Just remember, it's never going to be perfectly normal because our data is discrete and normal distributions are continuous, okay? And nothing is ever perfectly normal in the real world. Therefore, the mean of the sampling model, so all of those possible values of 100, found the mean of all of them, put them in a graph, okay? And then I found the mean of all of them, the mean of all my means, so it's sort of like a double mean. So you found a whole bunch of means, and then you find the mean of all of those means. That's going to be equal to the true population mean mu. Okay? And the standard deviation is the population standard deviation divided by the square root of n. Okay? Now, just remember, when you do the population, or when you do the standard deviation, the population has to be 10 times the sample size in order to prove independence. But you're going to prove all your conditions before you even go through and doing the question, so it won't be a problem. Okay, so summary, we're going to continue with our summary. So central limit theorem. Number one, make sure it's an SRS of size n from any population whatsoever, doesn't matter what it is, with mean mu and standard deviation sigma. When n is large, the sampling model of the sample means X bar is close to normal. So if you take large enough samples and find the mean, put all those means on a graph, that's going to be approximately normal. With mean of population, okay, it's going to have the mean of the population mean. The standard deviation divided by the square root of n is your standard deviation of your sample means. Okay, and remember, the mean of the sampling distribution is equal to the mean of the population. Okay, now the law of large numbers is going to tell us that we draw observations at random from any population with mean mu. As the number of observations increases, the sample mean X bar gets closer and closer to mu. So basically, the law of large numbers just tells us when we increase our sample sizes, so instead of taking samples of 100, if we take sample size of 200, find the mean, put on the graph. Another sample size of 200, GPAs, put on the graph. Another sample size of 200. Since I increase that sample size, size, when I take the mean of all of the means, it's going to get closer to the true population.